Hello everyone, and welcome back to a new episode of Advent of Code 2016. We are going to solve problem 17 today. We're closer than I've been in a while to being caught up. Probably not going to get there tonight, but who knows, maybe tomorrow. Well, obviously, tonight's problem has already aired, right? I can't solve day... Tonight's problem is day 18. I'm not going to be able to solve that live. But, I mean, that maybe by tonight, I will be done with both of these, and tomorrow I could do this one, but I don't know, probably not. So, anyway, here we are, day 17. 2 steps forward. You're trying to access a secure vault protected by a 4x4 grid of small rooms connected by doors. You start in the top left room, marked S, and you can access the vault, marked V, once you reach the bottom right room. I gotta say, there have been a lot of puzzles this year where it's like a maze with hashes for walls. And as a player of roguelikes, I just have a natural advantage. I can easily read this grid. I know exactly, obviously a bit of an exaggeration. But it's just kind of funny that there have been so many. Anyway, we start in the top left. We want to get to the bottom right. Fixed walls are marked with a hash, and doors are marked with dashes or pipes. The doors in your current room are either open or closed, and if they're closed, they're locked, based on the hash of a passcode, your puzzle input, followed by a sequence of uppercase characters representing the path you have taken so far. So every time we go, say, right, we add an R onto the thing that we're hashing. Only the first 4 characters of the hash are used. They represent, respectively, the doors up, down, left, and right from your current position. Any B, C, D, E, or F means that the corresponding door is open. Any other character means that it's closed. So that's 5 out of 16, about 1 in 3 for any given door to be open if it were actually random. Of course, it's all deterministic, but from our point of view, it may as well be random. To access the vault, all you need to do is get to the bottom right room. Reaching this room opens the vault and all the doors in the maze. So they give some examples here, and they point out that you might need to backtrack into a room you've already been to because although you have been there, the path you took is different, and so different doors will be open. Fine. That's all fairly clear. And they ask, what is the shortest path? The path itself, not just the length, to reach the vault. But we're going to have to be tracking the path anyway, since it's an important part of the node, is how you got to that node, unlike all the other problems where it was like, if you get to the same state by 2 different ways, that's sort of the same and you shouldn't search it. Here, if you get to the same node multiple times, it's a different node, and so we'll just encode that as part of our node and not as part of the path or anything silly like that. The node objects will all just remember how you got there. Let's see, we're adding to the end. So it's a little bit awkward to use cons cells, I suppose. Is it actually? I think it's, well, we have to turn it into a string anyway. Yeah, since we have to turn it into a string, there's not much point in the efficiency of using cons cells to add, because we'll then have to just collapse it to a string. So forget it. All right. I was just thinking about whether we could do something a little more efficient, but okay. So here we are. Def puzzle input to. I always think it's a def and it's not. To be this. And let's go grab our search function from problem 13, I guess? Yeah. There it is, and we made one change to it, didn't we? We made it have a unique key. Yes, okay, good. I appreciate that. So now all we need is a node class that implements the methods that search wants, and we'll be done. So this is, I think, a time when directed search will be pretty helpful compared to a breadth-first search. A breadth-first search that just wanders around in the top left corner of the maze won't be too bad, but it'll definitely be worse than one that aims, that explores more closely nodes that seem like they might be closer to an end. So let's just find a class node, and it needs a constructor. And what does it need? It just needs two things: a tuple, chords, and path. Self.chords equals chords, self.path equals path. Def evaluate the self. This graph is 4 by 4. We will call the top left corner 0, 0, I suppose. I suppose that doesn't even really matter. Yeah, it does. So if self.chords equals 3, typing is hard, 3, 3, return succeed. If any of x less than 0 or x greater than 3 for x in self.chords, return fail. This means you've walked outside of the maze. Otherwise, return progress. Now, we could avoid ever walking out of the maze by checking before you go to a node, like before. So we could have this check inside of evaluate or inside of nexts, but it's going to be a lot cleaner to have it inside of nexts because we can just look at the resulting pair of coordinates rather than having different cases for up, down, left, and right in nexts. And it's not expensive to put something onto the queue and then like decide to leave it that it's no good. Import queue as well. So I think we need goal estimate of self to be let's see. We'll just say return abs of self.chords of 0. Oh, it's not. I don't even need to abs it, do I? Because we know we'll be at. We can't have gotten outside. We can't have gotten past the goal in either direction. So it's just going to be 3 minus plus. Actually, it can be just 6 minus self.chords of 1. Yes? So we are a distance. Our best estimate is always it is never any larger than 6. The worst we could be is the top left corner. And from the top left corner, it might take only 6 steps to get to the exit. You never know. So we just start with 6 and subtract how close we are in each of the two directions. And at 3, 3, the estimate will obviously be 0. Fine. Now we need nexts of self. So something that we need is a direction mapper here. Dirs equals down to, let's see, if we're making the top left corner be 0, 0, I'd kind of rather have a yx. It just feels more natural to think of things in a row major order. So down is therefore 1, 0, right? Yeah. Up is -1, 0. Left is -1. No, it's 0, -1. And right is 0, 1. So that'll be useful to have in nexts here. For actually, we can return something for let's see. Dir dy dx in dirs. And we'll need an if as well. Oh, where was how do you do MD5s? I forgot already. From MD5, import MD5. And let's just def hash of n to be MD5 a puzzle input plus s dot hex digest. Okay, great. So, what now? Next, it's a little bit tricky. I guess something we will need is we will definitely need to hash the current path. So, here's an idea. We will have a function that returns the list of open doors. Def doors of path to be return hash equals. Oh, I can't call it hash, can I? S. Ha! We did it. An easy name that can't possibly be confusing. Equals hash of path. So now what we need is for, let's see, for dir and, no, for dir I dir in enumerate of, what is the order of the directions here? Up, down, left, right. Oh, that's not quite the order I wrote them in, but it's close. UDLR. I guess UDLR with single quotes here. If S of I in B, C, D, E, F yield dir. Oh, dir is a special. D, I guess. Sure. And in fact, instead of yielding D, let's yield a tuple of D and dirs of D. So that we can just use that in our next function. We can just call doors. In doors of self.path. Yes, that's good so far. So that actually takes care of the doors being locked. You know, we already filtered for doors that are not open. I'm surprised that it indents to here and not to like inside of the list. Huh. All right. Well, does that change it? Yes, it does. Interesting. All right. So what exactly do we need? We need a new node. No, we need a tuple because this thing wants us to give it a weight, right? And the weight is first, so 1 and node of yx equals self.coords. y plus, wait, what arguments does node want? It wants the coordinates first. So y plus dy, x plus dx, and also a path, which is self.path plus dir. Okay, that seems good. Are we done? Was that the whole thing? Does it compile? Well, it won't compile now. Pass. No. Or is not spelled with pipes. It is spelled with letters. There it is. Or. So this was a lot of code to write at once without testing any of it, huh? Yeah. Well. All right, let's just try it. Who knows? Let's see. What do we want exactly? We want vars of search of node of 0, 0, and empty. Right? Node has no attribute unique key. Yeah, you are right about that. We do not have an attribute unique key. Turns out we don't need it because we'll never, ever, ever run into the same path twice. It's just not possible. So we could remove that requirement. Remove the visited set. There we go. We must have a dict attribute. Uh-oh. Must have been none, huh? 10. Oh. It worked. Give me the 1th element and the path, please. It's this. That's exciting. That's the right answer. Thank you, search algorithm. All right, what's next? You're curious how how robust this security solution really is, and so you decide to find longer and longer paths which still provide access to the input. You remember that paths always end the first time they reach the bottom right room, so they can't ever pass through it, only end in it. What is the length of the longest path? Interesting. How do you... So we have to find all paths there, basically. I'm actually a little surprised there is such a thing as all paths. I guess if you just stumble around at random forever, you eventually get locked up in like a little tomb. But I'm surprised. I would think that you could just... that almost every path would eventually get you somewhere. Okay, I guess not. Well, tell you what, let's commit what we have. Day 17, part 1. So, how do we make it search for longer paths? At this point, A star is not providing us any help at all, right? Because we have to find all paths, and we want to keep the longest one. Okay. This is easy. It's so easy. Oops, I maximized the wrong buffer there. Instead of returning it, we'll just yield it. And then, so what we'll do is we'll print here search. Actually, solutions equals search of. What did we do in the REPL here? Search of this. Actually, let's say P1. There's not a good way to be able to reuse this iterator. There's a thing in itertools called T E E, which returns n independent copies of an iterator for you. And so that's great. We could use it to T the iterator and take the first one. And then search, like, just take the first of iterator 1 and then search iterator 2. But that's kind of silly because then it doesn't know we're done with iterator 1, so it has to keep the whole thing around. So I guess we'll just call list. Solutions equals list of search of this thing. And so we will print part 1 to be %s of solutions of 0 dot path, and then let's let part 2 equals, I think this is true, right? Help of Max, please. Takes a key if need it does. Let's see. So we want max of let's map lambda of x to x0 dot path first on this list, and then we can just print solutions 0. Max of solutions key equals len. Print part 2 %s mod, and let's just not even call it anything. Give me that back. Mod that. Okay. Python source.py. This is a little worrying. I guess a lot. Oh, yeah. I wonder. Oh, I see. I guess the search has to eventually terminate because eventually there will come a time unit where all 4 doors are closed. So you basically are searching by taking random turns up, down, left, and right. And like sometimes you terminate early, but most of the time you don't. But eventually there's some time when the first 4 characters in the hash. Oh no, because it's not a global hash. Right? You can change which doors are open by where you walk. It's not like there's gonna be some time where all the doors are closed, no matter what path you took. So I'm not sure why we're guaranteed that this terminates, honestly. You know what? Let's kill this right now so that we can get a little more introspection on how much progress it's making. And we'll just print yielding path of length %d. We'll call it cost, really. Cost mod. It's not mod, of course. New cost. Okay. So it's really starting to struggle now. But it certainly is finding these paths. I was going to say, it's strange that we're only seeing even numbers, But then I realized, of course we are only seeing even numbers, because each move either brings you one closer or one further from the exit, and we're 6 moves away. There's no way to ever take an odd number of moves and get to the exit. Well, it's starting to look like putting this all into a list was not a good idea, because there are a lot of them. Also, the A star search is actually costing us here, isn't it? Because it's making sure to sort them by size, which means it needs to keep a giant queue of like things to visit. Whereas if we were doing this depth first search style, we could just only have a single path in memory at once. Yeah. Okay. So I'm starting to think this is not the best way to solve the problem. Maybe it'll finish, maybe it won't. But in the meantime, I'm going to go and edit the program code and see if maybe we can just do it depth first in a better way. So let's see. Oops, don't type in that window. Yeah, also there's a problem that we're keeping all the paths of the same length, even though we only really need the max, because we put it into a list, right? We're keeping a lot of stuff in memory that we don't need. So let's just write a different I think we're just writing like not a search algorithm because it's really a traversal at this point. That just does things depth first. Even depth first is a little hard, isn't it? You have to keep like at each node that you're exploring, you have to remember like which of its children you are traversing into. Traditionally, depth first stores this on the stack, which I suppose is fine. On the other hand, we're finding paths that are hundreds of nodes long, right? Like how long are we now? 680? How does Max do with can I like look at the source of Max somehow? I want to know how it handles generators. Python Max generator. I would not be surprised to find it just works if there's an imax or imin or something. Okay, this is a really terrible Stack Overflow question. Let's try a different one. This pep in new generators, generator expressions. There's a pep something or other. Max. Reduce an iterable to a thing. Yeah, okay, cool. Yeah. So let's not make it a list. Let's cancel all this at least. It's not making much progress. And having to keep everything in memory has got to be pretty stressful. Tools.imap over this. Now it's not a list. And we'll print solutions is 0. We know it won't be the longest one, in fact. In fact, we don't even have to do a max by length. We know it'll be the last one, right? So for Solon in solutions, pass, print, let's see, solutions.next. Well, this will be name error iter tools is not defined. Import iter tools, please. Int has no attribute what? Path. Oh, no? Where is it? Where is it mad about that? Line 60, IMAP. It was right a minute ago. Oh, X1, not X0. Boy, I'm glad I cut it off. It was going to be... It was doing all this work to make the thing a list, and then I was going to map something over it that was going to break. Okay, so we're yielding a bunch of stuff. We still have the problem that that our A star is saving a bunch of stuff in memory that it doesn't have to. I don't know what Python's stack size is like. But I suppose we might as well get to writing a DFS def. That's not even really a, let's just call it traverse of a node. Let's in fact call it paths from a node even. So we don't need a queue. And we sort of need an unbounded amount of space to store all of the paths that we're in the middle of traversing. But it won't be nearly as large as the space taken up by the A-star approach. And I'll try putting that on the stack, because it's a little bit hard to transform depth first traversal into well, is it hard? Also, we will, if we do this, if we do it depth first, we will no longer be guaranteed that the last item in the collection is the most expensive one. But we can just put the max call back in. You know what? Actually, I think that we will take a break here before we get into implementing this paths function, since it may take a while and we're getting a bit late into the episode. So I'll end this episode, and then next episode we'll get to implementing an intentionally inefficient search algorithm. So I hope you guys have enjoyed this part 1 of day 17. Thanks for watching, and I'll see you next time.